Hello. I'm facing some camera issues, so I'm just trying to resolve that. Hopefully, we'll get started in a couple of minutes. Sorry about the delay. Hope you can hear me clearly and my screen is visible. Yeah, okay. Thank you so much for waiting. So, good evening. Welcome to the week 12 live session. So, as I said in the last class, you will have another revision class. I think I've given the date and time for that as Sunday. So, hopefully that works for everybody. If not, you can always watch the recording. So, I think that's going to be Sunday, I think 10 a.m., Sunday 10 to 12 noon. So what I've done is there were a lot of questions asked in the last class. This week huh, we don't have a problem solving component. I think you might have already noticed your topics, your table of contents basically says that you have federated learning for week 12, but as you've seen, the lectures all have moved to MLP and NLP, right? So we don't have any previous year's assignment questions. This year's assignment questions are all there is for this topic. So there's no point in discussing federative learning. Last time for the week 10, we did discuss some extra questions. Because you had already studied about DASK and all that in the lectures, I thought it might be slightly relevant. But this time, since we have not at all covered anything about federated learning in the course, we will not go through last year's week 12 assignments. That will not be helpful because it's out of syllabus. So if week 12 contents are clear, and I think the assignment also should have been out with probably a deadline sometime this week. So if those questions are not clear to you, then you can ask during today's session, and then in the revision class we can also go through questions that are not clear to you guys. Yes, good evening. So today also, in case you have any other doubts apart from the ones that were asked last week, you can put it on chat anytime during the session, and then we'll pick that in the next class. Week 11, sure, please post your doubt. So whenever you're posting a doubt, please mention the week and the question or the topic that you have a doubt in, and that way I can go back and refer to it from that week's course content. Link not working, I cannot help with that, unfortunately. PDF link, which link is this? The lecture itself, is it, or was it a link to a notebook or something? Or are you asking about the live session slides? PDF one last page. Okay, let me take a look at that. But this mostly I will not be able to resolve. Week 11. Let's take a look at that. Yeah, the lectures might have been recorded a year ago or a couple of years ago, so might have worked then and may not anymore be valid. So Let me take a look once. Week 11. This is the deep stream PPT, is it? The video analytics session 2. Is that the PDF you're looking for? Because I don't see any link in the last slide. Or the demo links, is it? Anyway, if it's a link in the course slides, I will not be able to help you anyway, since I don't have any of those resources with me. I have the same thing that you guys have. So please ask on the discussion forum, and hopefully the right people will see it and respond to you. If they don't, maybe mention it in the feedback form for that week also. So maybe NPTEL will look at it and contact the course instructors. So anyway, okay, this is a YouTube link. Yeah, this opens the deep stream video. Oh, the last couple of demo links. Yeah, if those links don't work, I think you'll have to ask on the discussion forum, and then you might be able to get the right links. Yeah, I see the slide that you're talking about, but unfortunately I don't have these with me either. So you'll have to ask on the forum, otherwise put it in the feedback form and hopefully they get back to you in time. Okay, so today what we'll do is, since we don't have a problem solving component, we will discuss all the doubts that you guys asked from the other weeks. And in the next week, other topics that you mentioned as not clear, we will discuss. So that's how it's partitioned. So feel free to add any other questions or doubts or things that you are not clear about in today's session also, and we can go over that next week. So we'll start with a recap of the NLP part and then move to some doubts you guys have asked. Okay, so here week 12 we went back to the language model side of things. So do not understand the smart city project. Which one was this again? Can you tell me a week number and a lecture number? If it's a demo video, it will be hard for me to help you understand, because I again don't have any of the code or the dependencies set up, so I'll not be able to run it. I might just be able to help you with specific parts of the demo that you did not understand. Smart city project. Which video in your lectures was this? Week 11. Okay, there's 2, 3. There are 4 videos here. So which video was it? And if you have any particular questions in that video, you can put it there, because 3 and 4. Okay, I'll see if I can summarize it for you, but that's like saying I don't understand half of week 11, right? It becomes hard for me to cover that much in a revision session along with 15-20 other topics. So if you can tell me what specifically you didn't understand, that would probably help us cover more things in the revision session. Used some file and opened it. Okay, I'll take a look at these videos and see if I can figure out which parts you have a confusion about, and then I'll see if I can help you with it. So you don't understand what file. Okay, you don't have the file. So if it's a simple video, you can look at what kind of a video it is, and try to get something similar from maybe certain data sets, or even a video from the internet that you can download and you can use it. Because from what I remember, I think it was an object detection demo. So in that video there is no proper show file. I don't understand what So this is a file apart from the video, not the video itself, is it? Didn't show the file. So by file, are you referring to the video that was used in this demo, or are you referring to a script or some code that was used in this demo? Maybe a file name would help me, because I have no idea if you're talking about some code snippet that was shown or a video that was shown, and without that I don't think I can go through the whole 2 videos in next week's class. So let's see, we'll come to that. Doubts in demos are a bit hard to resolve unless you have a very specific question. Okay, so I'll take a look based on your description and see if I can find what file it is, and then see. Okay, let's get started because we're 20 minutes into the session. So here we go into some more language related stuff, and then we look at some common large language models like BERT. So this is talking about the computational models of a word. So computational semantics basically is a way of doing things like reasoning or constructing a sentence based on the meaning, based on finding a representation for a particular natural language expression, right? And distributional semantics is based on the distribution of that word. For instance, I think you saw some examples about how often a word is found in a document, or how often 2 words occur together in a particular document, right? So these are statistical methods that study the usage of certain words in natural language and then try to do some things with that knowledge, right? These are 2 different ways of looking at it. Week 11, last video. Okay, sure. I'll take a look at this time and see if I can figure out what it is. Okay, let's move on. So talking about distributional semantics, right? Why are we doing this, or what is the intuition behind this, right? So so I would encourage you to kind of follow along with the live session, because if you're trying to find a particular point in a video or trying to find doubts while I'm explaining, then I'll have to kind of repeat it again. So maybe just like last time, today's break also can be 10 minutes, and you can take that time to find out whatever doubts you have and then put it in chat. That way you can focus on the session for now. And we don't have a lot of problems today, so taking a 10-minute break should be okay. We can do that. So here, this very simply was just talking about 2 different ways of reasoning about natural language or trying to understand natural language. One is computational semantics, the other is distributed semantics. Here you look at representing the meaning of a natural language expression. Here you look at it more from a statistical sense. You try to see how is this word used, or how it co-occurs with some other word, or things like that, right? So this is looking at things from a statistical perspective. Okay, so coming back here, so what is the intuition behind distributional semantics? So the broad intuition is that the meaning of a word is, like this quote says, right, is defined by its usage. So then again, how do we kind of reason about usage, or how do we understand usage? Usage is basically very contextual, right? So a word is defined by the words that are around them. That's broadly what is usage, right? So a word and its environment. So by doing some by finding some distributional metrics, for instance, which words occur together in a sentence or which words occur together in a document, you're trying to understand more about the distribution of that word, and thereby coming up with this distributional semantics model. So that's the idea behind distributional semantics. You broadly want to learn from how words are being used rather than just purely try to understand the meaning. So the context or the words along with which it is used defines that particular word. That's the idea for this. So now here are a few examples, right? Bergamot is a source of vitamin C. Flavor of bergamot is very fresh and mild. Bergamot is often used in oil, tea and jam. So here are the word that we are trying to understand about is bergamot here. So rather than looking at its meaning in a very abstract sense, we look at its usage. So this is one example of its usage, second example, third example. One simple thing you can do is to see what are the words, other words that occur in sentences with bergamot. So you might get words like this: vitamin C, flavor, fresh, tea, jam, oil, all of these, right? So that gives you something about this particular word's meaning. This is a distributional way of looking at it. Similarly, lemon is a rich source of vitamin C. Lemon has a refreshing flavor. Lemon is used in tea, jam, pickle, right? Now again, you could identify the neighboring words, and if you notice, there are a lot of common things between these two, right? So something you could do with distributional semantics and an analysis based on that is to say that bergamot is something very similar to lemon, and lemon is a citrus fruit, so bergamot is also a citrus fruit. This may not work in all cases, but here is something that you can do by doing an analysis of the distribution this way. So that's the idea. Okay, so now the next thing we try to do is to find a point in space based on its distribution. So I'm sure all of you have studied this in like basic geometry, right? So if we talk about 2 points, we first try to understand what is the distance between those 2 points, or how near are they, or how far are they. And you can do the same thing with vectors and all other mathematical quantities, right? So here we are trying to do something similar but for words. So one metric that you guys have already seen in this context is the Levenshtein distance. I think that was also asked as a doubt, so we'll talk about it a little more in detail today. But that was one very nice example where you could get a distance metric between 2 words. So here again the goal is to do something similar. So what you want is that similar words should be near each other in this space, this arbitrary space that we're talking about. And words that are not very similar should be farther away, right? So here for instance you see very good, amazing, terrific, nice, good, a lot of positive things. Here you see incredibly bad, bad, worst, worse, dislike, not good. So these clusters are kind of separated because they are different. But if you have words, so what you expect is words that are very similar fall in the same cluster, so they are near each other. Words that are very different fall into different clusters and they are far off from each other. Now this word basically has to be represented by a vector, right? So this is what this says: semantic content is presented by a vector or a word embedding. This embedding is obtained from the linguistic context of words. So this is what we've already been talking about, right? You want to get a vector based on the context or based on that particular usage of the word rather than the word itself. But ultimately you want something like a vector, because then you can do a lot of things like how far is one word from the other. Once you find a mathematical quantity to represent a word by, then you can do a lot of these operations, right? For instance, if I just tell you that this is 1 and this is 10, and I ask you what is the distance between these two, you might simply do 10 minus 1 or 1 minus 10 and give me a distance. That's the whole idea. You want to get to a vector. Yeah, now coming back to distributional representation of words. So this extends again the statistical models that we were talking about. So one thing you can think about it is a co-occurrence matrix. So here the matrix tells you about how often words co-occur together in a context, right? So here is two examples actually. Term document matrix, which tells you about the word occurrences in documents. So for instance, the word battle occurs 1 time in As You Like It, 7 times in Julius Caesar, and 13 times in Henry V. And similarly, good appears a certain number of times in this, certain number of times in this, and so on. Another way you can look at a co-occurrence matrix is word occurrences with neighboring words. And here we look at one word. For the way to interpret this is, you have cherry on the column here, and how often cherry co-occurs with maybe aardvark is 0, with computer is 2, data is 8, pi is 442, sugar is 25. So this tells you something about what cherry is, right? And similarly with strawberry, digital, and information. So looking at what words this co-occurs with tells you something about the word itself. So for instance, cherry co-occurs a lot with pie and sugar. You might conclude that this is one ingredient that goes into a dessert, right? That is a valid conclusion. Similarly, you see here digital with computer and data, right? Neighboring words means, so it can mean, for instance, I don't know how this is actually done because I haven't worked a lot with NLP, very frankly. So I can think of multiple ways to do it. One is you can just take immediate neighbors, right? Words that are just there next to each other. The other way to do it is to maybe say words that occur in a sentence. For instance, here, words that occur in a document, right? So if you have an overarching theme to the document, for instance, if this was a book about battle, then you would see a lot of battle related words co-occur in a document. A smaller window or a smaller interval over which you can do this is something like a paragraph or a sentence. And I think that it probably is done within a sentence, right? That's when it makes the most sense. Because in the same document, you can have multiple paragraphs or multiple chapters about multiple different things. So considering those as neighboring words may not really help. So it probably would be in a given sentence. But again, you can look that up and see what is typically done in NLP. Okay, so now like we were talking about before, we are trying to come up with a vector representation for a word, right? So going back to this co-occurrence word context matrix that we had, you can come up with a vector like this, right? So if I had your computer and data as 2 dimensions, I would represent information as those 2 coordinates, right? Basically your xy, whatever you do for every single point. So you have 3982, 3325. This is a vector in this space. Similarly, I could have digital with these 2 coordinates, 1683, 1670. But what is the problem with coming up with vectors this way? So one thing is, you might end up with very sparse vectors. Basically, you see a lot of zeros here, right? So you come up, because of that, your vector itself becomes very sparse. And because you have a lot of words, your vector becomes very high dimensional. So what is the dimension of the vector? So in the first example that we saw, which is the term document matrix, The dimension of your vector is the number of documents in the collection, basically this axis. If you think of this as the horizontal axis, this is going to be your dimension of the vector. So you'll have all of these as your axis, and any given word will be a combination of, will have components in each of these. That's how it's going to be. The other way you could do this is using the word context matrix, and there you might take something like the top 50k frequent words. For instance, I think here computer and data are not the top ones, but you could basically consider the top 50k frequent words while coming up with this matrix. So then again, the dimension of your vector increases a lot, right? And you will end up having very sparse vectors, because again, like you see in these examples, there are a lot of zeros, right? So it's a very inefficient way of doing things. So a denser representation like what is used in word2vec or BERT might be better in practice rather than going for something like this. Okay, so moving forward, so this is something that's proposed by a paper. So these are, so here we learn denser vector representations using a feed-forward network, which is basically a type of neural network. And you have two different models here, a continuous bag of word model and a skip-gram model. What is word2vec? I think some of these slides explain it. So let's wait till we finish the recap, and if you still don't understand it, we can go through it. So going back to these two models, so we have continuous bag of word and the skip-gram model. So in the continuous bag of word, what you do is you consider a context of a window. So this is basically like what we were talking about, right? So I can have my window or my context to be a sentence or a paragraph or a page, right? Or I can say it's of a certain fixed length m. So if I say 10, that means your context is 10 words. So you can imagine this window of 10 words moving, right? It slides. And in this case, what this model does is it tries to predict the center word. So given a window, you try to predict the central word in it. Okay, the skip-gram model tries to predict context words in a window of length m for a given word. Does anyone remember this one more clearly? I don't. So do any of you remember what is the difference between this and this? Maybe this predicts multiple words in a window of length m for a given word. So you have a target word here. Okay, I see. So this is kind of the reverse, I think. So correct me if I'm wrong. I don't remember this part. So here what you do is you take a given word, and again you have this notion of a window of a certain length. So let's say the window is of length 5. So you're trying to predict what are words that could be in this window. So that is based on the context. So here you're considering a plus or minus 2 word window. So here are all the things that you could come up with. Yeah. And the objective here is to learn the weight parameters again for the network. Okay, so here, so going back to this, so we predict the central word given the context of a window of length m. So this is, and or you can have the other one, which is your skip-gram, predict context words in a window of length m for a given word. So for both of these we saw examples, and this gives you a static embedding of for a given word. So that's the only thing. So I think that's what was said in the lecture also. So we discussed earlier here that we want a vector that is that captures the context for a given word rather than the word itself. So one way I can come up with a vector is just have a static vector for every word, right? The other way is to consider the context of the word and then come up with the vector. So these are two valid ways of doing it. So this method comes up with a static embedding of the word, which is not very good. But on the other hand, it's very fast to train. Yeah. So moving forward, so the embeddings that you get on a particular word, the same word, changes over time, right? Why does it change over time? Because the language itself evolves, technology evolves, so the language first of all captures reality at that particular time. So depending on how reality changes, the language and the usage of a particular word itself may change, right? So you see three examples here. So gay in the 1900s was referring to things like tasteful or flaunting. Gay in the 1950s was referring to things like witty and bright, pleasant, cheerful, right? Whereas a lot of us who live in the post 90s world know of gay as a gender or sexual identity related term, right? So you can see how the word itself has evolved. So if you train a model on data from this time period versus data from this time period, it will need to capture that difference in meaning, right? So you see what could be a problem of a static embedding, right? It may not capture this kind of an evolution with time. And you have some more examples of words here. Awful, for instance, used to talk about solemn and majestic, more in the sense of awe, right? AWE. So that's the awful context there. Whereas awful in the recent terms has been referring to horrible or terrible, and more lately it probably has been used in the context of weird or wonderful. So the word itself has changed a lot. And similarly, you have for broadcast, I think it's more of a technology evolution, right? So broadcast in the 1850s is talking about seed and sowing seeds and scattering seeds, whereas broadcast in the 1900s and later is talking about different communication media, television, radio, newspapers, and so on. So this is something that didn't even exist in 1850s, and you'll see this used a lot, right? For instance, the word neuron might have been used only in medical or say an anatomy or a physiology context, mostly a medicine context, right? And then once neural networks came in, the neural word and the context and its usage has changed a lot. And that's something that happens as a consequence of technology evolving or words being reused to mean something else. So from different decades you get different meanings, and this shows that trend of meaning shifting. So yeah, relational properties in embedding space. Yeah, so you see that there is some words have a relation. For instance, in this figure, I think the relation is the capital of each country: Italy, Rome, Greece, Athens. So there is some way of, if you were to think of this, there is a way to kind of connect these 2 points. Here in this case, it might be slightly different. Woman, man, heiress, hair, and madam, sir. So different gendered words for the same thing. So these are all properties that kind of need to be there in the embedding space also. I think it's a picture quality, or maybe zooming in helps. Yeah. Anyway, the original one of this is there in your slide, so you can take a look at it. This is just talking about some properties that are there in the embedding space. Okay. Then coming to various biases, right? So again, something that happens with neural network training is a lot of biases that are present in the real world kind of get amplified. This is what has been observed. So gendered terms, for instance, become more gendered in the embedding space than they were in the input text statistics. For instance, your text may be biased to a certain extent, but the way you're doing this embedding is somehow amplifying that bias. That's what literature tells us. For instance, this word to vec trained on news text has a lot of gender bias. For instance, when men is associated more with a programmer and women is associated with a homemaker, and father is associated with a doctor, mother is associated with a nurse, right? Similarly, you might have ethnic biases. So this has a problem. So all of these biases are not theoretical, right? Because we are talking about using these models for various applications. For instance, I might use this to do some kind of allocation. Say that maybe it's a CV selection kind of thing, right? Or any other. So an application of these models will basically suffer from these biases, and therefore the application itself will suffer. Here, for instance, the representation of different communities is not very good. So African American names had a higher cosine with unpleasant words, whereas European American names had a higher cosine with pleasant words. So this is also a problem. So your language model may learn that certain surnames are associated with bad things. Maybe it's something like crime or robbery. Or this bias is similar to ML. Yes, it's kind of the same thing. All ML models roughly suffer from the same bias. It may vary depending on the techniques that you use and the models that you use, but I don't know if it's always amplified or that's specific to MLP, but definitely all of it suffers from the bias that's there in the data. If you have bias in the data, the model will definitely learn that bias. Something you can do is to try and find data that removes these biases. Then again, the question is, your model may be very different from reality, right? So one approach could be to retain as much bias as is there in the real world. But then again, the question is, do you want your model to make the same mistakes that human beings make, right? So these are complicated things that come into the umbrella of AI ethics and biases and things like that. These are just some examples for you to understand what is that. So here we talk about gender and ethnic biases, but there are a lot of other subjective biases that human beings suffer from. Okay. Today maybe we'll take a slightly earlier break. So maybe we'll take a break now for 10 minutes, because I think we have just a couple of recap slides of BERT left, and this is a good point to stop and then resume. So again, please use this 10 minutes to see if you have any doubts, and put those doubts on chat. We will discuss them in the next session, which is your last session. So I will not be taking any questions in that session, because I usually prefer to have slides ready for a doubt, right? That way it's easier for you to understand. It's also easier for me to convey whatever needs to be conveyed. So please put any doubts that you have in today's session itself, and those will be the final doubts that we'll deal with. And since your exam is coming up pretty soon, I'm sure all of you have started revising and started learning. So yeah, you can do this. What is self-supervised? So I'm guessing you're asking about the earlier slide. We can talk about that after the break. And in the meantime, please put any other questions you have. So we'll resume at 7:55. Okay, I see that we have a couple of questions. Week 11 last video. Okay, week 1, what is privileged or non-privileged mode of PM? Sure, we can go through both of these next session. So yeah, I think there were a couple of doubts on this. So what is self-supervised, right? So word to vec is what we are talking about here. So first of all, I hope you've gotten what is word to vec by now. If not, it learns this vector representation for a given word, right? As the name itself suggests, it takes a word and it converts it to a vector. That's the simple idea. But this may not be done directly, right? If you noticed both the methods that we spoke about, the continuous bag of word method and the skipgram method actually try to do something else. For instance, this one tries to predict the center word, this one tries to predict the context words. But in this process, they're also coming up with a vector representation for a given word, right? That is your word to vector. Now, why is this self supervised? It is self supervised because it kind of learns by itself without needing this external labeling or annotation of data. So here, for instance, you take a sentence, everything that you need is available within the sentence itself. So for instance, here you're trying to predict apricot, right? The center word. You already have it as part of the sentence. So in that context, it is self-complete. So it need not get any other external labeling or annotation. The sentence or the text itself has whatever is needed. So it can predict the center word and compare it with the input text. In that context, I think it is spoken about as being self-supervised. So hope both these are clear. Now let's go back to the BERT part of it. So again, we are not going too much into the details of the architecture of BERT. So we'll just go through this. So the base model of BERT has 12 layers of transformer encoder blocks with 12 multi-head attention each. So if you need to understand a little more about all of these, again, models like BERT are very popular today, right? So you can just look up BERT architecture and you'll find a detailed diagram along with an explanation where each of these are explained in detail. But for now, we'll just think about this as a model architecture. So BERT stands for bidirectional encoder representations from transformers. And this masked language model is a very important part of how BERT is trained. So what is done here is 15% of the tokens are input tokens are sampled from training, 80% are replaced with some mask, and then 10% are replaced with randomly selected tokens, and 10% are left unchanged. And the task is to predict the masked token. So you can find some similarities of this to your continuous bag of word, right? You're trying to predict the word, and in that process you're trying to learn some things. So here also it's kind of the same, except certain other things are done with the data. But overall you're trying to predict the mask tokens. So that's what is shown here also. So this is again the masked language model. So you can see the input here. So the sentence actually reads, "So long and thanks for all the fish," but you can see the long is replaced by some mask, right? So for instance, you can take this to literally be mask right now. Thanks is also replaced by mask, and some words are randomly replaced by something else. The is replaced by apricot. So this might be the equivalent of doing something like a crop with your images, right? So remember when we spoke about vision models, we spoke about random crop, where you take one given image but you crop it in different random ways, and your model learns from all of those different random things. How does that help? It helps in the model being more robust to maybe your angle of the photo variations, or partially the object partially being visible and things like that. So similarly, these two changes are kind of done. This 10% with randomly selected tokens, I'm guessing, is done to help the model be more robust. But this is kind of the masking and the training with this masked language. And here is an example for a sentence prediction task. So this is with training BERT, then once it is trained, you can also do some fine tuning, right? So you basically take BERT and you might want to do some specific task with it, right? So based on your task, you will add an output layer that takes the contextualized embedding from BERT and converts it to the desired output. Now you have this model because you added this output layer, right? So now this extended model, which is basically your base BERT plus your output layer, you can train it with task specific label data. So now there might be labeling involved depending on your downstream task, right? Whatever you're trying to do with BERT. So that might need labeling, so you'll feed in labeled data if needed, and the whole thing will be trained. And then this will help it learn additional parameters that may be application or use case specific. And this portion, which is kind of frozen, so let's say this part is the original BERT, right? So if I kind of freeze this part uh, and then add another layer on top of it, and then do a training of this whole extended model, there may be some minimal adjustments happening to this layer also based on some parameters, but this output layer will basically be whatever is helping you do your particular task. That's the idea of fine tuning here. And text classification is one such example. So what is text classification? Given a document and a fixed set of classes, right? So just like you were given an image and maybe a fixed set of classes, a simplest one is animal classes, right? You're asked to say, is it a dog, is it a cat, is it a horse? So similarly, you can think of some classes here, and then you have a training set. So now notice that you need to label these documents. For example, here you will need to say document 1 belongs to class C1, document M belongs to class CM. So this is no longer self-supervised, right? So you will need to do this manual labeling and feed it into the classification model as such, which may be BERT with an output layer. What is the output layer here? I don't know if that was discussed. I don't actually remember. So I just remember that there is a task specific output layer that's added. So if one of the others remember what the output layer is, you can answer. Otherwise, you can go again, look this up. Transformers and language models are very famous right now, so you should be able to find it. So the output here is a a classifier that can basically take a document and give you a class. Example is a movie review like this. And your classes are positive and negative. So here your input is this zany characters and richly applied satire and some great plot twist. So the output, as you see from the color, is positive. And the other review says it was pathetic. The worst part about it was the boxing scenes. Again, as you see from the color, this is classified as a negative review by the classifier. So this is an example of an application that you could do with BERT. And I think there was a demo video, right? So the demo video should have hopefully told you what is the output layer that you add. You can rewatch that and see if you find that detail. Okay. So with that, we come to the end of the recap session for today. So again, I told this in the beginning, but since some of you have joined later on, I will repeat it. A lot of our doubts were asked last week. So what I've done, since we don't have a problem solving component, because last year's week 12 was on federated learning, and questions from last year are also on federated learning, but this year we no longer have federated learning. So we will not go through those assignment questions. Hopefully the week 12 assignment is easy to solve. If you guys have any questions on the week 12 assignment, you can post it on chat and we can go through that also in the next class, which is our revision class or the last class. Doubt in deep stream code that is not defined in video. Again, I'll need like a very specific timestamp or okay, you're saying that's not part of the video. So what exactly is your doubt? If it's relevant to the course and what we do, then we can look at addressing that. So we'll again follow the same format that we do. That is, I'll ask you the question and you can come up with the answer, and then we will look at how to solve it, right? Since these were part of previous week assignments and you guys didn't understand that. Okay, sir has text file. Okay. So you're talking about some input text file. If you can give me a timestamp on the video, I can go look at it. But if it's an input file that's not linked or not given to you guys, I don't think I can find it either, because I don't have anything more than what you guys have. So you should ask it on the discussion forum, and hopefully the instructors see your message. If it's just an input file, then I don't know. I don't have the link to that. If it's some other line of code that you don't understand, then we can talk about it. Okay, with that, we will move to the question side of things. Okay, what is the Levenshtein distance between the words root and route if the replacement cost is 2 instead of 1? So I guess you guys have already solved this assignment. So any answers to this? Three. Okay. Anyone else? Okay, no other answers. I'll give you another 30 seconds. Some of you may be trying to solve this. So okay, if there are no answers, we can look at it. So before I go to the matrix approach that you kind of saw in class, let's talk about a simple thing that we can do, right? Because one is understanding the matrix and how to fill that matrix. The other is, from a time perspective, is there a quicker way for you to solve this question? So a Levenshtein distance is again an edit distance. Basically, if I had to change this word into this word, what is the cost of that, right? So basically now I'll talk about a very simple and intuitive thing that you can do, right? So R is the same here, O is the same here. So till here you need to do nothing. Now you need to replace this O by U. That is one thing. After that, T is the same. You need to do nothing. After that, you need to add an additional E. So you have two operations here. Replace of O by U and add of E. So there's nothing here. You add a T here. Now, in the matrix and in the example that was discussed in class, all of these operations had a cost of 1. Now, in that case, the answer would have been 1 plus 1, 2. Now, what is being asked to you is, if it is a replacement operation, the replacement cost is 2, the addition cost is 1. Addition cost remains the same. So, what is the new cost that you have? 3. So, based on this, the answer to this question is 3, right? So this is a very simple and intuitive way of solving this question. Is this clear? First, only then we will move to the matrix based approach, because that takes a little more time. Okay, this is not clear. Okay, let's try that again. So I have 3 operations that I can talk about here, right? First, there is add. So if I have nothing, I can add a letter there, right? In this case, I'm trying to add a E. This word is 4 letters. This word is 5 letters, right? So I'm trying to add a letter at the end. That's one operation. I can also delete um, a letter, that's another operation. So for instance, if I was trying to go from route to root, I am deleting a letter, right? That's another operation. The third operation is replace, which in this example, I am replacing O by U. So here you're neither deleting nor adding, you're instead replacing it, right? Now each of these have an associated cost with them. In the simplest example, we will assume that the cost associated with all of them is the same. The cost is 1 each, right? In that case, what are the operations I need to do to change from this word to this word? I need to do one, so observe that let me write this again, ROOT is your source and ROUTE is your destination. And let's maybe draw a sort of grid so that you can easily look at what's similar and what's not. So these two are similar, right? You need to do nothing. This is different. O needs to change to U. So this is a replacement operation. So this is one operation we need to do. Let's continue. The T is same in both cases, so you need to do nothing here. Finally, there is nothing here and there is an E here. So you need to do an add operation. So the two things that you need to do are a replace and an add. So in the original case where all of these cost 1 unit each, your cost would be 1 plus 1, which is equal to 2. In this case, you are told that the replacement costs 2 and nothing is said about the addition, so we'll assume it still costs 1. So 2 plus 1 is 3. So this is the answer to why it is 3. Now is this clear? Okay, great. What is Levenshtein distance? It is edit distance, right? So if I had to edit this word to this word, what is the cost of that operation? So again, this cost is a mathematical thing, right? So we need to ascribe some mathematical weights or costs to each of these operations. So if I were to describe it to you, I would say the way to do this is add one letter, replace one letter. But we are talking about a distance metric, saying that if I were to edit this word to this other word, here is what it's going to take. So then I have to come up with some mathematical quantities that represent these operations and then do a sum operation on those quantities to kind of have this idea of clubbing multiple operations. That's what we do. So Levenshtein distance is a metric that tells you the cost of changing from one word to the other. Hope this is clear. We will spend a brief amount of time talking about the matrix. You may not understand it. And it also takes a lot of time to fill this in. So I would recommend trying this way for most words. If it looks very complicated, then you can try this. So here also the idea is the same. So what we are trying to do is use dynamic programming to come up with a closed form expression for this. So here we are trying to go from cat to Kate, right? So the matrix based approach tells you to do this. So you write cat along one axis, Kate along the other axis, and then you come up with one empty column and one empty row, right? This is basically you have nothing and you're trying to add this, right? So you have nothing and you're trying to add K, so it costs you 1. You're trying to add A, it costs you another 1, T, E, right? Something like that. So you add these empty rows and columns. This is kind of your initialization condition that you need for the dynamic programming to work. Now, how do you fill these elements, right? So now here is an example, right? Let's look at that particular example itself. So we are trying to fill this question mark element 1, 2. So what are we trying to do there? We are trying to calculate the distance of C to Ka, right? So what are the options that what are the operations that are involved there? So notice that you can have multiple ways of getting to this point. So you have multiple choices. Of course, we want to take the choice that has the minimum cost. So here, one option is replacing C with A, add cost of 1, and distance of empty string with K. So this is one option. So you can work this out to understand this better. So this will give you a cost of 2. Other thing you could do is to delete C, which adds a cost of 1, and then you have an empty string now, and then you add K, right? That totally gives you a cost of 3. The third option that you can do is you insert A, which adds a cost of 1, and then you do a replacement of C to K, right? This also gives you a cost of 2. So now your minimal cost is what you will kind of calculate. So these are your 3 options, right? And you have a direction associated with each also. Pay attention to this. So a replacement is always a diagonal thing. A deletion is along the y-axis, and an insertion is along the x-axis. So these are the 3 choices that you have, right? And in each case, you take this element and add a +1 to it. You take this element and add a +1 to it if you're doing this operation. If you're doing a replace operation, it will not cost you anything if both are equal, right? So if xi equal to yj, then you simply stick to the diagonal element that you're comparing with, right? It would be the same. If the two are different, then you would add a 1 to the previous element you're comparing to, right? So in this case, for instance, it would be filled up with I think 2, but you can work that out. So it would be the minimum of all of these, and then you can use this to come up with that. So this is how you do that. So is my voice breaking for everybody? Anyone else? Can you please confirm? Is the audio clear or is it breaking up? Okay. Did everyone else hear this part of the explanation, or was it lost? Okay, I will give you a brief summary of it. Okay, I see a raised hand. Could you please type on chat whatever your question or doubt is? Okay, so the brief, I'm not audible. I think that's only for you because I don't see anyone else saying that. Please try to rejoin the meeting and you should be able to hear me. And please check your speaker settings. Okay, so let's go over this briefly again, right? I don't want to take too much time with the same thing because we have multiple other things to discuss. So as I was saying, so here we are looking at cat to kate, right? So you have 3 possibilities. If I look at this particular term that I'm trying to fill, I have 3 ways of doing it, right? So you can map those 3 ways to directions. So for instance, the replacing is along this direction. So here what I'm trying to do is to replace C with A, which adds a cost of 1, and then I have an empty string which I try to add K to. So that gives me a cost of 2 because the replacement itself costs 1 and this cell says 1, right? So it becomes 2, and then the deletion operation which the previous cell, so remember that the delete operation is along the y-axis, right? So you should be looking at this term. So here the cost is already 2, and then you have a deletion cost. Why would you have that? You can read this, that will explain it to you. So the cost becomes 3, and along this direction you have the insert choice available to you, and then you have 1 here, and that adds a cost of 1, which becomes 2. So these are your 3 things available, and obviously you want to pick the minimum of these, so this will be populated by 2. Why are you replacing C to A? K is also there. You can try that out and see if you have multiple ways, and you basically have to look at this part and this part and see what each term in the matrix means, right? And if you're talking about this term, you can look at what the elements here are, right? So C and A is what you have, right? So that's what you're trying to do, whereas here you have an empty string and K. So that's why those operations are mapped to those things. So you have to look at that particular column and row and then see what you're trying to replace or what you're trying to add. And in a replacement case, it can be different because the 2 elements can be same or they can be different. So the 2 elements are the same, your replacement cost is a 0. So you don't need to add anything to it. Whatever is along the diagonal, you take the same thing. If your 2 elements are different, then you add a cost of 1. That's basically it. So I would suggest you take an example like this. So this is completely filled out, but don't look at this and try to fill it on your own, right? And then you will understand. Try to ask yourself as you fill each box, what does this represent, right? So for instance, this C to K, what does it really represent? And then you will understand some of these things. I don't want to spend more time on this because we have multiple other questions as well. If we have time at the end, we can come back to this. Let's do that. Okay, next question. Which of the following sentences have potential structural ambiguity? She met some friends on a trip. She was going to the bank. She made her a duck. A, she met some friends on a trip. Okay. Anyone else? C, she made her a duck. Okay. C, she made her a duck. Okay. Anyone else? Okay, let's look at the answer. So let's look at the recap part of it, right? So these were the various types of ambiguity we saw. So the question asks about structural ambiguity. So in that context, let's look at the structural ambiguity example. It says she saw her with a binocular on the hill, right? Now, what is structural ambiguity in this context? So you can interpret it as her with a binocular, as in this person, let's say A, was looking through a binocular and saw another person B, right? Or it could mean that B had a binocular, right? So the structure of the sentence lends some ambiguity here. That's the challenge that you have here. Now going back to these three examples. So she was going to the bank. I think none of you have said this as the answer, so this is probably very clear. There is no ambiguity at all here, right? Now C looks like, for some of you it looks confusing. So she made her a duck, right? So if it is structural ambiguity, you must be able to come up with a different ordering of the sentence where that ambiguity is clearer, right? So for instance here, the problem is she saw her with a binocular on the hill, right? Now if I rewrite it as maybe she saw her using a binocular, then it becomes clearer, right? Now here the ambiguity may come in from what, who is being referred to when you say her, right? But that's not a structural ambiguity. There's nothing about the structure of the sentence itself that lends this ambiguity. But if you look at option A, she met some friends on a trip. So now you can interpret it as the friends were on the trip, or this person met friends while she was on a trip, right? So there is something about the sentence structure that leads some ambiguity here. Is this clear as to why the answer is A and not C? Okay, good. Okay, let's move to the next question. Learning rate of a neural network is 0.1 and the mini batch size is 32. If the mini batch size is multiplied by 2, what will be the learning rate? 0.1, 0.2, 0.01, 0.05. Okay, we have some answers saying B and also one saying A, B. Okay. Okay, let's take a look at the answer. So let's recap on this. So in this lecture about convergence in week 8, so we spoke about learning rates for large mini batches. So remember that the mini batch size is a hyperparameter. So changing your mini batch size also changes the learning process itself. So what is done to have good convergence while changing the mini batch size is to also scale the learning rate. How do you scale it? There is something called a linear scaling rule, which is very simple. When you multiply mini batch size by k, you also multiply the learning rate by k. Both are linearly scaled. Yeah. So here the mini batch size is 32 and the learning rate is 0.1. If you multiply the mini batch size by 2, you also multiply the learning rate by 2. So 0.1 into 2 is 0.2. Is this clear? Any doubts here? Clear. Great. Let's move on in that sense. Which technique can be used to reduce generalization error? Ghost patch normalization, gradient clipping, hyperparameter tuning, data augmentation. A, ghost patch normalization. A. Any other answers? Okay, no other answers. Let's do a recap of what ghost patch normalization is. So again, it's from the same techniques for faster convergence, right? So batch normalization is a technique where you're trying to increase the robustness of a neural network and improve its generalization. But batch normalization uses the batch statistics. So it depends on the batch size that you choose, right? So instead, what is done in ghost batch normalization is you have this notion of ghost batches or virtual batches instead of the real large batch. So by operating on these ghost batches instead of the actual batches, you overcome this dependency on the batch size. So that makes your model more robust or more generalizable. So coming back to the question, what can be used to reduce generalization error is ghost batch normalization. Hyperparameter tuning is not one of them. Hyperparameter tuning is more of coming up with things like your learning rate, your batch size, and it's not in the generalization error side of things. Same for gradient clipping and data augmentation. I'm not sure if you've studied gradient clipping in this course, but yeah, it doesn't have anything to do with generalization. So hope what ghost patch normalization is and how it reduces generalization error is clear. I'll move to the next question. If you have any doubts, please ask. So, how many hours for 3 epochs of training are required when the total training samples are 80,000, batch size is 50, and time taken for each iteration is 30 seconds? So, someone said they had a doubt with this. So, I'll give you 1 minute to work this out since this is numerical. So, you can take your time and let me know when you have an answer. Okay, we have one answer saying B, 40 hours. Anyone else? D, okay. 15 hours. D, 15 hours. I'll give you a few more seconds. B, 40 hours, okay. Okay, let's take a look at the answer. It is B, 40 hours. So let's talk about why this is so, right? So I don't know if this is visible. Yeah, maybe better now. So the batch size is given to us and the total number of training samples are also given to us. So the number of batches that it takes is the total number of samples divided by the batch size, which is 80,000 by 50, which comes to 16,000. And you're told that, so this iteration may not be very clear, but in this context, it refers to the time per batch. So that is 30 seconds. Now you're asked about the time for 3 epochs. So first let's calculate the time for 1 epoch. So remember that 1 epoch is 16,000 batches. So time for 1 epoch is time per batch into number of batches. So 30 into 16,000, which comes to 48,000 seconds. Now you're asked in hours, so you need to divide this by 3600, which comes to 40 by 3. This is the time for one epoch. So the time for 3 epochs is 40 by 3 into 3, which comes to 40 hours, which is option B. So now is this clear? Or does someone still have doubts with this? It's clear. Okay, good. Let's move on. Consider a 39 cross 39 color image and a CNN with no padding in each layer. At layer 1, there are 10 filters of size 3 cross 3 with stride 1. What will the input size to layer 2 be? 37, 37, 10, 29, 29, 3, 32, 32, 10, 17, 17, 10. You asked this question? Sure. Anyone else who has answers to this? A 37, 37, 10. Okay. Anyone else? I'll give you another 30 seconds because this also involves some amount of calculation. C, okay. Anybody else? Okay, let's take a look at the answer. So first of all, stride and padding are mentioned here, right? So let's make sure to understand that. So here's what padding and stride look like, right? So when I say padding of 1, this is what that means. So you add one row and one column to your image and then you apply your filter on top of it, right? And so here we are talking about a 3 cross 3 filter, and each iteration of this filter will give you one cell in the output image. That's kind of how it is. So you can see that mapping here. So similarly, when I talk about stride equal to 2, that may not be clear from this figure, but what I mean is, so along this direction, if I were to draw the next position of the filter, so this is where it is right now. So I take a stride of 2 along the x-axis. This is what it would look like, right? Okay, just assuming it's a 3 cross 3, this is what it would look like. So a stride of 1 would mean it would overlap like this, right, after one element. So stride is the way the filter moves, right? So you have the size of the filter. If I say stride equal to, let's say this is a 3 cross 3 filter. So when I say stride equal to 1, that means the next position of the filter. So stride in common English refers to, for instance, your footstep, right? Stride length, right? So the next position of the filter, if stride equal to 1, is one column offset. If stride equal to 2, it's going to move by 2 columns. That's what stride means, and this is what padding means. Yeah, step size is a good definition. So now that we understand both of those, so first I'll give you a formula that will kind of quickly help you calculate this, but try to also understand the intuition behind doing that, right? So here you're told that the input is 39 cross 39, padding is 0, stride is 1, and the filter size is 3 cross 3, and there are 10 such filters, and you're asked what is the input size to layer 2, which means it's the output of layer 1, right? So if I draw this, this is what it would look like. So I have some dimension input image, and I have a certain layer. And then I have layer 2, right? I'm asked what is the input to layer 2, which is basically the same as the output of layer 1. So you have your input, you have layer 1, you're asked to calculate the output of layer 1. So the formula looks like this: 1 plus the input image dimension minus f plus 2 star p divided by s, where p is your padding, s is your stride, f is your filter size, right? So your input size is 39, filter size is 3, and padding is 0, stride is 1, right? And if you do that, you get 39 minus 3, which is 36 by 1, which is 36, plus 1, 37. So the height and the width of this output will be 37, right? This is the formula based thing. Now what I would recommend is simply take a 9, maybe a 9 cross 9 image, right? This sort of thing, and give yourself a filter size. Try to work this out, right? Why do you get this? For instance, why is it divided by stride? Why is it plus 2 star p, right? So if you look at the way padding is, you kind of understand. Even when I say padding equal to 1, I'm adding one row here and one row here, one column here and one column here. So overall, you know how you get this term, right? So it's more important for you to understand how this comes, because in case you forget this, you will be able to derive it on the fly, right? So I would suggest working this out with a small example. You can take a 3 cross 3 filter. You can initially set your stride to maybe 1, padding to 0. Just see what output you're able to get, and based on that, are you able to derive something like this, right? So you basically need to figure out how many times the filter moves, right? That would give you, to cover the entire image, that would give you the number of output elements, and the height or the width. Once you do, the other dimension will remain the same. So that's pretty straightforward. So you just need to figure this out, and then you can add in these dimensions of padding and stride and see how it changes. So if you remove the padding and stride for this formula, it just looks like this: 1 plus input minus filter size. So try doing that, see if you're able to get that. Then you can include the padding and stride in a micro example and see if you're able to understand these terms. This will really help with your intuitive understanding of how these layers work. But for now, at least I hope that this explanation is clear and it gives you an idea of how to get better at this. So with that, we will move forward. This is a very similar question. I think someone asked this also. Consider what is the difference between padding and stride. Padding is this, right? Where you pad your image with some extra columns and rows. Stride is the step size by which your filter moves. They are completely different and unrelated. This figure will help you understand both of them. Okay, moving back to this question. Consider a 16 cross 16 color image and a CNN with padding in each layer. At layer 5, there are 12 filters of size 3 cross 3. If we apply 9 filters of size 5 cross 5 at layer 7, then what will be the input size to layer 10? You have 4 options. Any answers? D, need more information. Anybody else? D, need more information. Okay. Okay, D. Anyone else? Okay, let's take a look at the answer. It does need more information simply because we already spoke about this in the previous question, right? So if I'm given a layer and I'm given the input to that layer and the description of that layer, I'll be able to say what's the output of that layer. So now you're given something about the input, you're given something about layer 5, and you're given something about layer 7, but you're asked about the output of layer 9, right? So you don't have the information of the rest of the layers to kind of get this. So you will need more information to figure out this part. So that's the answer. So is this also clear? Yeah, no problem about that. You can watch the video to catch up. I think we just went over this question in 2 minutes. So that's okay. You don't understand. Okay, it's very simple. So given a layer and its input, you can tell what is the output. So here we are given the input image, which is basically the input to the first layer. Then we are given some information about layer 5 and layer 7. We are asked about the output of layer 9. We cannot say that unless we have the information about all the layers that come in between, because otherwise you don't know the input to the layer, you don't know the description of the layer, so you can't come up with the output of the layer. Therefore the answer is need more information. Okay, any other questions on this? Not okay. I don't know how else I can explain this to you. So what is your confusion? Let's try that way. No, like what do you not understand? Because I have given you the same explanation 2 times. So, okay, padding and stride. Okay, let's go back to that. So, padding is talking about adding some rows and some columns to your image, right? Let's take a very simple example. So, I have an image and I say padding equal to 1. What that means is I'm going to add this one row and column everywhere, right, to the image. So if I say padding equal to 2, I'm going to add 2 rows and columns to the image. Now if I say stride, I'm talking about how the filter moves. So I have this as my filter. If I say stride equal to 1, that means my filter is going to move in step sizes of 1. If I say stride equal to 2, then it means that my filter is going to move in step sizes of 2. So this is the difference between padding and stride. Is this clear? Okay. So hopefully your doubts are resolved. So I think that was the last question. Yeah, that was the last question. So yeah, what is the next part of it? The formula you will have to work out, try that out and then come back, right? Again, this is not an undergraduate level course, it's a graduate level course. So I expect all of you to put in effort to understand something as well. So go try this out. It's not very difficult, right? Take an example and work it out. The formula is already given to you. So try and understand how it comes and take examples so it will become clearer, and try to derive this formula on your own. So I can only give you the formula and give you an example for it. You can try this out on your own, and doing this on your own will help you understand it better. So that's something I will give you as homework. You can go try that out after the class. Yeah. So I think there was one other question in the Levenstein distance. And since we have some time, we can go look at that. Let's go back to the cat to Kate, right? So I think the doubt was in the replacement part of it. So here we are talking about this term, right? We are talking about this 1, 2 term. Now how we look at this is there are two operations that are part of this, replacing C with A. So if I'm talking about this element, the row corresponding to it is C and the column corresponding to it is A, right? And this is a replacement operation. And because I'm looking at the substrings I'm looking at are C and Ka, right? So one is the replacement operation of C to A, the other is the addition operation of an empty string to K, right? So the empty string to K, the cost for that is 1, and then you have a replacement cost, right? So when we say diagonally we go like this, we are talking about this cost and then the replacement cost, because this is your original element from which you are trying to predict the cost of this element, right? So the cost of this original one itself is 1, right? How is that 1? You're trying to go from an empty string to K, and that is an addition cost, that is 1. After that you're trying to replace C with A. So you've added K to an empty string and then you do a replacement of C with A. Why you do it this particular way is very simple. You look at the matrix and the elements you're trying to fill. So if you're looking at C and A, you are basically replacing C with A. That's all it is. It's nothing else. So that's why that cost is 1. This cost is 1. So 1 plus 1 will give you a cost of 2 when you look at the replacement choice for this element. Hopefully this is also clear. And again, this one will become clear if you work out this entire matrix, and each time you try to fill in an element, ask yourself, what does this mean, right? For instance, you are filling this element. We are trying to basically look at the distance from C to Ka. And just the way you are looking at minimum across all three to pick this, that's how you will do it for the rest of the matrix too. And the final element is basically talking about the path of minimum cost that you use to go from cat to kate. So that will tell you the overall edit distance or the overall cost to go from this word 1 to word 2. So once you work that out, you will kind of understand it better, right? So in one case, this is a corner case, right? For instance, so this replacement, so we have A here and A here. So now if you look at the replacement cost, xi is equal to yj, and that's true. So your cost is 0. So you just take the diagonal element cost and put it there. Whereas if these two were different, then you would have added a 1 to it. So that's a special case for replacement. So hope all of this is clear. So yeah, you need to practice these things because it's a bit complicated. So you need to week 12. Okay, I'm guessing this is an assignment question, so maybe we'll discuss it in the next revision class itself, because by then I'm guessing the assignment deadline will also get over. So we can definitely discuss it in the next class. Okay. Sure. So how do we calculate the rank of a tensor? Is this based on any particular week's questions? That will give me context on where, what part of the lecture or what part of the course contents you have a doubt on. If not, if it's a general question, you can also say that, and then if I have extra time apart from all the questions that have been asked about the course, I can try and answer this one. So our next class will not be at a regular time. You will get an email on that, but I think it's Sunday 10 a.m. So 22nd 10 a.m. will be the next class. So you can accordingly plan, but you will get an email. Week 5 question 6. Okay, I'll take a look at that too and then put that in. Okay, rank of tensor. I see. Okay, we can do that. Doubt in deep stream coding part. Again, if this is the file that you were talking about, I don't know what I can do about that. You need to find the file that's missing, and only then you'll be able to run it. So see if you can find similar examples on the internet. Maybe that will help. Okay, we have another couple of minutes. Any other final doubts before we wrap up? Like I said, whatever you ask today will be the final ones that I address. You don't understand the entire deep stream. Like I said, that's harder to address because I have around 20 doubts that people have asked on pointed areas. So that itself will take the 2 hours that's there for the next session. So explaining an entire topic all over again may not be possible. So if you have particular things that you don't understand, it'll be easier to go through. If not, you can always watch the videos that are already there and try to understand it. Very, very important. So are all the lectures in your course, right? So no different from anything else. Which things are important? Again, I don't know that. Everything is relevant in terms of your exam. So there is no such thing as the most important topic or a topic from which most questions will be asked. So pay attention to all the topics. In coding, again, that would depend on what you're trying to do. So I can't say that without really looking at the application. Okay, so if there are no other questions, we can wrap up right now and then we'll meet for our final class. All the best for your exam preparation, and yeah, hope things are getting clearer with these live sessions. So see you in the next class for our last revision session. Thank you so much.